Welcome to the Deep Dive, where we cut through the noise to get straight to the insights. You know, when I first started exploring AI and machine learning, I kept wondering, why can't they just use normal version control? Like, what is it about these AI files that makes them so tricky compared to regular code? So today, we're diving into something maybe a bit behind the scenes, but honestly, it's absolutely critical, how these massive AI models and data sets actually get stored and managed. Our sources for this deep dive really highlight the unique problems with handling these huge, often binary files you see on places like the Hugging Face Hub. And our mission today, it's really to unpack why the old ways, well, they just weren't cutting it, and how this revolutionary new system is changing the game, making things faster, collaboration smoother. We'll trace the evolution, from the older Git LFS system right up to this new approach called XSET, looking at the specific benefits. And as we get into this, I think you'll really see why understanding this stuff isn't just for tech nerds. It gives you a real edge if you're working in this space, managing projects, or honestly, even if you're just curious about what powers modern AI.
That's a great place to start because, repositories on the Hugging Face Hub, they're fundamentally different from your typical software project. It really boils down to two main things. First, the files are just huge. We're talking gigabytes often, sometimes even terabytes. The sources mention a few files hitting the terabyte scale.
Oh, terabytes, okay.
And second, they're binary, meaning, not human readable like code. Think safe tensors files, Parquet datasets. Trying to jam those directly into a standard Git repository, it doesn't work.
Why not, exactly?
Well, think about cloning a Git repo. Git pulls down the entire history, every version of every file. Now imagine that for massive binary files, you'd be forced to download gigabytes, maybe terabytes of old data you'll probably never even look at. It's just prohibitive.
Right, that makes sense. Completely impractical.
So the Hub's initial solution was quite clever, actually. They decided to use Git, modern version control, but keyed the actual data somewhere else. Remote storage, like Amazon S3.
Yeah.
And in the Git repo itself, just small pointer files and a special .git attributes file to manage it all.
Oh, okay. So the Git part stays small and fast.
Exactly. Kept workflows pretty efficient, considering the limitations.
So dealing with these huge binary files,
Yeah.
Git LFS was the first real answer on the Hub, wasn't it? For listeners who've maybe bumped into it, how did Git LFS try to tackle this?
It did. Yeah, Git LFS, or large file storage, basically followed that same pattern. It also used S3 for remote storage, and it relied on that .git attributes file to tell Git, okay, these files are big, let LFS handle them. For those large files, LFS creates a tiny text file in the actual Git repo, a pointer file.
Okay.
And that pointer contains metadata, basically instructions on where to find the real file in S3. It includes things like a SHA 256 hash.
Which is like a unique fingerprint for the big file.
Exactly, a unique ID. It also lists the pointer size itself, and importantly, the size of the actual remote file in bytes. That's useful for checking things, managing storage.
That does sound like a pretty smart way to keep the main repository manageable. But, well, if it worked, what was the catch? What was the fundamental problem?
The big one, the real Achilles heel of Git LFS, is its file-centric approach to deduplication.
File-centric, meaning?
Meaning any change to a file, no matter how tiny. If you tweak just a few bytes in a multi-gigabyte model, LFS treats it as a completely new version of the entire file.
Oh, so you have to upload the whole thing again? Every single time?
Every single time, the whole file. Uploading when you commit, downloading when you pull. Think about iterating on a model, making small tweaks.
That sounds incredibly painful, especially for large models.
It is painful. It leads to a really frustrating developer experience, huge amounts of duplicate data piling up in storage, and it just slows everything down. People would avoid committing small changes because the upload would take forever.
Wow, yeah, I can see how that would be a massive bottleneck.
Yeah.
Okay, so LFS was a step, but clearly not the final answer. What was the next leap? How did Hugging Face move beyond that?
That leap is Zet. And it's a big one. Hugging Face actually acquired the company behind it, ZetHub, back in August 2024, specifically to replace Git LFS on the Hub.
Ah, interesting. So they brought the tech in-house.
Exactly. Now, on the surface, Zet-backed repositories look similar. They also use S3 underneath. They use a .git attributes file.
Yeah.
The Zet pointer file even contains all the same info as an LFS pointer, plus one extra field, a Zet-backed hash. But the core innovation, the thing that changes everything, it's byte-level deduplication.
Byte-level. Okay, so not the whole file anymore. How does that actually work?
Precisely. Forget file-level deduplication. SE operates down at the byte level. It uses a technique called content-defined chunking, or CDC.
CDC, content-defined chunking.
Right. Basically, it breaks the file down into small, variable-sized pieces called chunks. Think around 64 kilobytes each, typically. Each chunk gets identified by something called a rolling hash. It's a clever hashing method that's resistant to insertions or deletions. So if you add data in the middle of the file, only the chunks around the change are affected. The hashes for the unchanged parts stay the same.
Okay, that sounds much smarter.
It is. So when a client that understands, it's X, we call it a data-aware client, updates a file, it chunks the new version. Then it checks which of these new chunks are already in the exit storage system from previous versions or other files. And here's the key. It only uploads the chunks that are genuinely new, the ones it hasn't seen before.
Whoa, so if I only change a tiny bit of a huge file.
You only upload those few tiny chunks, not the entire gigabyte file. This dramatically cuts down on network transfers.
That is a game changer for workflows. I can immediately see how that speeds up iteration, updating models, adding rows to datasets.
Exactly. For those common workflows, incremental updates to checkpoints, appending data, inserting data, the speed difference is huge. It makes collaborating so much smoother, too.
How efficient is it, really, like with these chunks?
Well, the new chunks get grouped into bigger blocks, around 64 MB for efficient uploading. And they're stored just once in what's called a content address store, or CAS. Think of it like a giant library where every unique chunk has its own address. The Hub currently recommends keeping files under 20 gigabyte, for instance. At a 64 KB chunk size, a 20 gigabyte file breaks down into about 312,500 chunks. But across versions, maybe only a few thousand or even just a few hundred actually change.
So you're only ever transferring that tiny fraction. That's impressive.
It really optimizes things.
Okay, this sounds incredibly efficient, almost like magic for large files. Is there any downside, any scenario where this chunking might add overhead or complexity? What's the trade-off?
That's a fair point. The overhead of the chunking process itself is generally very, very low. It's heavily optimized for these large binary file types common in AI and ML. Where you might not see as much benefit is with, say, lots of very small text files that change completely each time. For that, traditional Git is still perfectly fine. But for the scale we're talking about here, models, datasets, the byte-level approach of JETS is just overwhelmingly more efficient. The main thing, really, is just making sure you're using a client that knows how to speak Bizet to get those chunking benefits.
Got it. That makes sense. So if you're listening and thinking, okay, I want this efficiency, how do you actually start using Zet? How do you adopt it?
Good news there. It's actually becoming the default. As of May 23rd, 2025, all new users and organizations created on the Hub get Zet-enabled repositories by default.
Okay, for new accounts, what about existing ones?
For existing profiles, so users and orgs created before that date, you can opt in. There's a sign-up process to make Exit the default for you, and then your existing repositories will get migrated automatically in the background. Oh, and a little perk. PRO users and Enterprise Hub organizations get fast-tracked access to the migration.
And the installation, is it complicated?
Nope, super simple. It's usually just pip install -u Hugging Face Hub. If you grab version 0.32.0 or later, it automatically installs the necessary component, H5xe2. That's the client, written in Rust for speed. And if you're already using popular libraries like transformers or datasets, they depend on Hugging Face Hub, so chances are you might get it automatically when you update those.
Okay.
If for some reason you're on an older version of Hugging Face Hub, specifically between 0.30.0 and just before 0.32.0, you just need one extra step. Pip install -u hf-xe to get the client explicitly. But for most people now, just updating Hugging Face Hub is enough.
Simple enough. So once you have it installed, are there any best practices, tips to really get the most out of Exceed in your day-to-day work?
Definitely. A few key recommendations. First, obviously, use the HVAC client, either directly or through Hugging Face Hub. That's how you get the chunk-based performance. Second, you can actually tweak HVAC using environment variables. If you've got a lot of network bandwidth or a powerful machine, you might be able to speed up downloads and uploads even more, worth looking into if performance is critical for you.
Okay, good tip.
Third, embrace frequent, small commits. Because Gets only uploads the changed chunks, committing often is really fast and doesn't waste storage. So commit early, commit often.
Makes sense. Break down the work.
Fourth, be specific in your .jit attributes file. Don't just use a wildcard like dot for LFS exet. Use precise extensions like .safetensors, .bin, .parquet. This helps make sure only the truly large files get routed through X, keeping things optimal. And finally, think about access and organization. Because Ake makes transferring large files so much more efficient, you don't have to compromise as much on how you structure your repositories for size reasons. You can organize them logically for your collaborators and the wider community, making it easier for them to find and use your work.
Those are great practical tips. Now, it sounds amazing, but like any new tech, I assume that isn't quite finished everywhere yet.
Mhm.
Are there any current limitations people should be aware of?
Yeah, a few things are still in development. The HXAC client, the Rust one, currently needs a 64-bit system, so older 32-bit architectures aren't supported right now.
No.
Also, support in JavaScript libraries, specifically HuggingFace.js, is only partial at the moment, and full support for uploading files directly through the web interface is still being worked on.
Support for hosting eggs-backed repositories in the EU region is planned, but is not available just yet. And finally, deeper integration directly with the Git command line client, something called GitZ, is also still under development. So you mostly interact via the Hugging Face Hub library for now.
Right, so a few areas still evolving, but what about compatibility? If I'm using an older tool, or if some files in a repo are LFS and some are EEGs, does everything break? That's actually one of the really well thought out parts. The transition is designed to be seamless. Eggs storage still uses the standard Git LFS pointer file format. So fundamentally, if you're using a tool, you don't necessarily even need to know if Gets is working behind the scenes.
Ah, that's crucial.
Absolutely. Older clients, like previous versions of Hugging Face Hub that aren't set aware, can still interact with Eggs-backed repositories. You can even have a mix of classic Git LFS files and new Vix-backed files within the same repository.
How does that work for downloading then, if the old client doesn't understand chunks?
There's a clever mechanism called the Git LFS bridge. If a Z-aware client asks for a file, it gets the efficient chunk data and reconstructs it locally. But if an older, non-Z-aware client asks for the same file, the bridge steps in. It reconstructs the full file on the server side and gives the old client a single, standard download URL, just like it would expect from traditional LFS.
Very neat, so it handles both cases transparently. What about uploads from older clients?
Similar, seamless fallback. If a non-Z-aware client uploads a large file, it just follows the standard Git LFS upload path. Then in the background, a process on the hub automatically converts or migrates that LFS uploaded content into a proper get-backed revision later on. This means repository maintainers and everyone using the hub can adopt XZ at their own pace. Your old scripts won't suddenly break. It avoids disruption.
That sounds like a very smooth rollout plan. And quickly, any security considerations with this chunking and deduplication?
Yeah, they've addressed that. The deduplication uses cryptographic hashing, and it's done in a privacy-sensitive way. The system ensures that you can only ever access and reconstruct files for which you have explicit permission. You can't somehow use the chunking mechanism to see data from files you're not supposed to access.
Okay, that's reassuring. So wrapping this up, what's the big takeaway here for our listeners? For you working in AI, I think the key thing is that EZ is a really significant leap. It's tackling that fundamental bottleneck of managing the enormous data that fuels modern AI. It's not just about saving disk space or download time, though it does that brilliantly. It's really about enabling faster cycles of experimentation, making it easier to share and build on each other's work. Ultimately, it helps accelerate the whole pace of AI innovation.
Absolutely. And maybe a final thought to leave you with. Think about the shift. Moving from versioning whole files to versioning tiny bytes within those files, especially for this kind of large, constantly evolving data. How might that change not just AI development, but how we think about versioning and collaborating on any kind of complex, evolving digital asset, models, data sets, maybe even other things entirely? What new possibilities does that kind of granular control really unlock for you to explore in the future?